So in this video, we are going to discuss layer normalization. When we are training these neural network models, sometimes they become unstable. If you've done deep learning, you know something called vanishing gradients or exploding gradients. Because as you train these models, they pass data through towards the end of the model, and then they calculate something called a loss function. And when they calculate something called a loss metric using a loss function, when they calculate that loss metric, then they back propagated that what they've learned from the loss function, from the loss metric, back into the model, updating weights back into the model. So the weights are updated or the parameters are updated based on the results of the loss function or based on the loss metric. But sometimes that grad the and the way they do that is using gradients. But sometimes the gradients become very, very small that it's difficult to update them. I gave an example where maybe the gradient is now 0.00000001. So updating that, it might lead to 0.00000005. It's very small gradients that then become difficult to really work with, making the training very, very unstable, or they explode, which is called exploding gradients. So the two problems are exploding gradients and vanishing gradients. So we use layer normalization to try get rid of this and improve stability and efficiency of our training mechanism. What we will do is we'll adjust the activations or outputs of a neural network layer to have a mean of 0 and a variance of 1. What do we mean? Let's actually write what we mean here. So just imagine that we have a neural network layer here. That is, these are the inputs 0.11, 0.12, 0.36, and 0.24, and then we have minus 1.19. So those are the inputs of a neural network layer. And when it goes there, imagine now these are the outputs 0.22. So this is the layer. This is a layer with five. Let's just say 5 nodes. 0.22, 0.34 on 6 nodes. 0.00, 0.22, 0.00, and then 0.00. So when you look at these, the mean is 0.13, and the variance for these outputs is 0.39. So what we'll then do is we'll add a normalization layer here. So we are going to add layer normalization. We want to normalize these outputs. So if it's a fully connected layer, all these will be connected, right? They'll be connected like this. I'm not going to draw all of them because it just take time. As I'll have to draw something like, what is this? 5 times 6, which is like 30 lines. I'll have to draw 30 lines, but they are all connected like that. So when we add the layer normalization to these outputs of that layer, we will now get maybe the 0.22 is now converted to a 0.61, and then this 0.34 is now converted to a 1.41. This 00 is converted to minus 0.87. 0.22 is converted to 0.58, and here we'll have a minus 0.87 and another minus 0.87. So now when you look at this new layer, this one here, it is now mean equal to 0.00 with a variance equal to 1.0. This variance is also called unit variance. Unit variance. This improves our training and improves our like training mechanism and the stability and all of that. Let's just see how that happens in code, because that is our section that we're doing now. So before we jump into that particular code, I just wanted to emphasize one part. Let's go back. So you see here, when we're doing that backbone, when we're doing the backbone, we said, okay, the backbone is going to have a dummy layer layer normalization here, the final normalization is going to be here, and we defined it here. So now we are going to fill in this dummy layer norm which calculates the mean and the variance, and then converts that the layer and a layer's output to have a mean of 0 and a variance of 1. So let's see how that happens. Let's just, here we are just creating an example. Let's say we just create an example with two training examples and 5 dimensions, like we had in our in when we're writing in manual, when we're writing in right in smooth draw. So now this is one training example. This is the second training example. We will calculate their mean and the variance in these two lines. What we did there, as you can see, we did dimension equal to -1 because we want to calculate by the columns. So going across like this, that's what we're doing. So that's why it's dimension equal to 1. If we had dimension equal to 0, it was going to do by the rows. But here we want it to say calculate the mean through the column, which means it's per row, per row, per row, per row, per row. So the first one is this mean, and the second one is this mean. And this is the variance of the first training example. This is the variance of the second training example. Well and fine. Now, what will then output? We will output, it is out minus. Um, so here, our output that we have, these ones here in our training examples, right? We'll then say the output minus the mean divided by the square root of the variance here, like this. So that's what we're doing. Um, That's what we're doing there. As you can see, subtracting the mean and divided by the square root of the variance centers the inputs to have a mean of 0 and as a variance of 1 across the column and dimension. So that's what we have there. Cool. So these are now the normalized. We just print them out. These are the normalized outputs after we have applied that normalization. And we can check that the variance and the mean. Let's now calculate the new mean and the new variance and print them. We see that this is a very, very small number. So the mean is essentially 0 for the first training example here that has been normalized. And the second one, we see it's also a very small number. So it's essentially equal to 0 as well. And the variances are equal to 1. So we've normalized that layer. Here we're just making sure that it prints nicely. So let's update our dummy layer normalization that we had. So we're just going to put an epsilon, and there's good reason for that. We're just going to put a very, very small number. And these scale and shift, they also help in training. We didn't talk about them, but they help in training. It's just parameters that are added that are learned by the model. The model will actually adjust these parameters as it is training. They just help with stabilization as well. But the most important part is this part here. The mean, we calculate the mean. So whatever x that we put into this forward, or whatever x is there in that layer, or the output of that layer, we then calculate the mean using that dimension again, dimension equal to -1. The variance, again, we do that, and then we just normalize it. So whatever we had as the output of that layer minus the mean divided by the square root of the variance. Here we are adding this small epsilon because we just want to avoid dividing by 0. Because imagine if the variance was 0 and we didn't cater for that, we would have divided by the square root of 0, which is 0, and then we get an error. So we just add a very, 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 very tiny number here just to make sure we don't divide by 0. That's it. And then we just return this. We'll scale the normalize and then just add a bit of shift. These two, don't worry about them right now. If you don't understand them, we're not going to really get into the detail of why that works, but they help with training the model itself. And they're learned during they're actually optimized during training, um, which improves the model's performance. So cool. So now what we'll have is we will now instantiate the layer normalization object. Here, we're saying embedding equal to 5 because you remember our output in our example that we had here. Our output, sorry, I'm not going to run it. Our output, remember our example here, we had we had 5. Our output, our output here, we had 5. It had one, two, three. No, it had 6. So what we are, let's see. So yeah, we're going to embed it into 5. And then when we get the batch examples, so output, we apply our batch examples here using now our layer normalization. That is everything, instead of us doing it like we're doing it manually here. So you see, we're doing step by step and all of that, but now we have put it into our layer normalization class. So let's apply this class. Let's see what will happen. So we apply the class to our batch example, which is, okay, I was mistaken. Our batch example, you remember our batch example, where is it? We created our batch example somewhere up here when we were just starting. Uh, we created our yeah, we created our batch example here. This is where we created our batch example. So applying our layer normalization to that batch example, this output, these layers, these sequential layers, they output like 6 nodes, like we saw manually here. Cool. That's why I was getting confused with the. I was getting confused with the. I was getting confused with that part, with that 5 and 6. But here we're just saying the input is going to be 5, and then it will output that 6 that we had at the top. So now let's apply that layer normalization to the batch example. So it's going to get that batch example. When it gets the batch example, it's going to calculate the mean. It's going to calculate the variance. It's going to return with a bit of a shift. Now, what it has returned, this out, what it has returned. Let's calculate its mean to confirm that our layer normalization class is working. You see that the mean is actually 0, and the mean for the second example is 0. And the variance for the first example is 1, and the variance is 1 as well for the second example, which means our layer normalization is doing exactly what we wanted to do. Perfect. We have done the first part of our transformer block, normalization. Let's move on to the second part. As you can see here, we're now talking about GELU. So let's see what GELU does.